Hello everyone, it's Mr. Neighbor here, and we're talking about Chapter 16, Sound and Light. The first section we're going to deal with is point 16.1, which is sound. So a couple things about sound waves. Sound waves are longitudinal waves, so that's the compression wave we're talking about. It's not the transverse wave, which is this. It's the compression wave where you have compressions and then the points where there is less particles together right there. So it's a buildup. They're being compressed, and that has to be compressed through some material, through some medium. So if there is no medium, you don't have sound waves because it's something called a mechanical wave. So mechanical waves need a medium to transfer the particles through. So that means in space, there is no sound because there is no medium for the particles to travel through. Light is not a mechanical wave. Light does not need a medium to travel through. Sound does. So in different mediums, sound travels at different rates. In air, it travels at 345 meters per second. In water, 1,482 meters per second. And in steel, 5,960 meters per second. The speed ultimately varies from a number of quantities. It depends on the medium: air, water, steel, gas, liquid, and solid. The temperature, hot or cold, how dense something is, and the elasticity of the material. So let's look at each individual piece of those and see how sound is affected by them. All right, first, elasticity. Elasticity is the ability of an object to bounce back to its original shape. Sound travels faster in more elastic objects. Typically, gases are the least elastic, liquids next, and solids are the most elastic. So think about metal and think about water. Water, liquid, less elastic than steel or metal, which is more elastic. So sound travels faster through the metal. Density, generally speaking, in a material of the same state of matter. So if you're comparing to solids, if you're comparing to liquids or comparing to gases, when you have material in the same state of matter, the denser the medium, the slower the sound travels. So sound travels slower in lead than it does in steel because lead is more dense. So more dense, less speed. And temperature. The higher the temperature, the faster the speed of sound because the particles are moving faster. Higher temperatures excite particles so they can move fast. Colder temperatures slow down particles so the sound will move slower. Sound intensity. Intensity is how loud a sound is. It depends on the amplitude of the wave and the distance from the source. So if you're looking at a sound wave, the bigger the wave in amplitude, the more intense it is, the louder it is. It's measured in something called a decibel. So 0 decibels is the threshold of hearing when you can start hearing. 50 decibels is a normal conversation, and 100 decibels is when you start to feel pain. So that kind of gives you an idea of the decibel scale and how loud something is. The frequency is how high or low the pitch of a sound is. That depends on how fast the particles are vibrating, the frequency. So frequency, as we've learned in a previous chapter, is measured in hertz. So infrasonic, that is less than 20 hertz, and that's too low for the human ear to hear. The human range of hearing is between 20 and 20,000 hertz. And ultrasonic is over 20,000 hertz. That's more suited to bats hearing. That's too high for us to hear. So the hertz, that is how compressed that wave is. That's the frequency. Because remember, frequency is how many times that wave duplicates in 1 second time. So higher frequency means that that duplication is happening a lot faster. And that's how high the pitch is. So frequency is the pitch, and the intensity deals with the amplitude of the wave. So let's look at a few practice problems. Here we have 2 sound waves, and we want to know which sound is louder. So the loudness, the intensity, is all determined by the amplitude. So which of these has the highest amplitude? I would say B has the highest amplitude. So this one is louder. Let's just answer the question of which has a higher pitch. So a higher pitch would mean that the waves are compressed more. There is more frequency. So which one has a higher pitch? Well, this wave starts here and then duplicates right here. This wave starts here and duplicates itself right here. So this has the higher pitch. So this one is louder, and this one also has the higher pitch for B. Another two examples. This one asks for what the higher pitch is specifically, but let's do both, starting with the pitch, and then we'll go into the loudness. So the intensity. Higher pitch, though, that deals with how many times it's duplicated in 1 second. So the ones that are more compressed are going to have the higher pitch. So here it starts, and here it duplicates. Here it starts, here it duplicates. This will be the higher pitch. And then intensity, that means amplitude. So which one has the higher amplitude? That is also A. So this has the higher pitch and is the loudest of the two. We're going to finish up this video with how do you hear the parts of the ear. So this is a general diagram, and we're going to go into the specific parts and their purposes next. So first we have the outer ear. So the outer ear consists of the pinna. That's the ear flap, also known as the auricle. Auricle is how you pronounce that. That is used to focus the sound waves into the ear canal. Okay. The external auditory meatus, that is the hole through the temporal bone that opens the space for the ear canal, middle ear and inner ears. The auditory canal, or the ear canal, focuses the sound onto the eardrum, and the tympanic membrane, which I'm going to move my face, is the eardrum. So this is your eardrum. That ends the outer ear and begins the middle ear, and that's where sound starts to vibrate. Sound starts the eardrum vibration. So sound makes the tympanic membrane vibrate. Next, we have the middle ear. So the tympanic membrane is when the outer ear stops and the inner ear begins, and it starts the eardrum vibration, causing 3 of the tiniest bones in your body to vibrate, one after the next. So these 3 bones are the malleus, that is the hammer part, the incus, we call that the anvil, and the stapes, which is the stirrup. The stapes is right here. So what each of these do, the hammer vibrates the anvil, which vibrates the stirrup, which vibrates the oval window of the cochlea. So the cochlea is right here. And then we have the eustachian tubes. That is the tube that connects the middle ear with the pharynx. This allows the pressure on both sides of the eardrum to equalize. Lastly, we have the inner ear. So the cochlea. That is a long fluid-filled tube folded in half and coiled up like a snail shell. This is the cochlea. The entire surface is lined with cilia, which are tiny, tiny hairs. So the cilia, the little hairs, are connected to nerve fiber. Once the little hairs are vibrated, the nerve sends signals to the brain recognizing the sound. Lastly, we have the semicircular canals. These are 3 canals in 3 different planes, able to determine body position in space and maintain balance. So these are the semicircular canals. A little bit more about the cochlea. Low-pitched noises are registered in the inner part of the cochlea. Notice that it's 500 hertz, then 1,000, then 2,000. So sound goes in this way, and if it's a low pitch, it'll be recognized here. Higher pitches will be recognized here. So as you age, these hairs right here, they don't operate right, or they break. So then there is no signal being sent. So you don't hear higher pitches. Also, if you're exposed to a lot of high pitches, these hairs might break. And when they break, they don't send signals. And when they don't send signals, you don't hear those higher pitch anymore. So don't have too loud of high pitched sound near you. And that's the basic of the ear.